So welcome everybody to second day of Verycrypt tutorial. We had a lovely day yesterday where Cass Kramers described Tamarin, and then Bruno and Benjamin described CryptoVeriff. There was a lot of activity on Zulip. So let me remind you again, all questions will be asked and answered on Zulip. Regularly, the speaker will look at Zulip and also take your questions from there and answer them live. But please log into Zulip and ask your questions over there. The first tutorial of the day is F-star, which is going to be headed by Asim Rastogi from Microsoft Research in India. And he's going to be assisted by Marina Polubaleva from INRIA in Paris. So without much ado, let's let Asim take this away.
Yeah, thanks, Karthik. Thanks everyone for joining us on the second day of the Verycrypt workshop. Hope everyone is having fun. So I'll start with sharing my screen again. Okay, so this, as Karthik mentioned, this session is going to be about doing verified crypto with F-star. Marina and I are going to co-present the session. So quickly, some logistics. The total duration of the session is 2 hours and 30 minutes, and roughly this is the breakup that we are planning for. I'll start with the basic introduction to F-star. That should take around an hour, where I'll introduce basic concepts and basic proof strategies of F-star. We'll take a 10 minutes break where either it's just a break or we'll see if there are questions on the Zulip chat that we can take. Then I'll go into low-level programming in F-star for about half an hour, take a 10 minutes break again, and then Marina is going to finish with HACL star and actually showing you some crypto verified in F-star. So I think Karthik already mentioned, but I had the slide. So please ask questions on Zulip. We have several experts around who are really F-star experts and will be able to help out. Sean, Natalia, Denny, Je, and Theo, and actually many others that I may be forgetting here. There's also a Zulip topic titled Questions for Speakers in the F-star stream. You can post any specific questions that you have about talk or slides that you would like to see addressed in the Zoom session, and if possible, we'll take it up during the break. And finally, I would say, please keep updating your GitHub repo for your local copy of the tutorials GitHub repo. We push some new exercises, examples, so just do a Git update for that. Okay, so let's start. So before I start, some acknowledgements. The work that we are going to present is joint work with several of our collaborators at Microsoft Research in Redmond, Cambridge, India, INRIA Paris, University of Argentina Rosario, CMU, UC Davis, and many other academic institutions. This include, we also had many interns and external collaborators who have contributed to the project. These are the URLs where you can, so F-star is a open source project on GitHub, and there's also a dedicated website that has tutorials, papers, links to previous talks, and so on. So feel free to check out these resources. Okay, so what is F-star? F-star is a programming language and a proof assistant. So it's a functional programming language with effects, meaning that its syntax and the basic concepts are similar to other functional languages like OCaml, F#, and Haskell. It has primitive support for effects, meaning that you can write not only you can write functional code, but also imperative code that has effects that modifies state, that throws exceptions, that may diverge, and so on. It's a semi-automated verification system that uses SMT solver at the backend. So the proofs that you do in F-star are assisted using an SMT solver, and we use Z3 at the backend. So in that sense, it's similar to other tools like Daphne, Y3, Pharmacy, and Liquid Types, etc. But at its core is a higher order dependent type theory, and that makes it closer to proof assistants like Coq and ACTA. And it also has a meta-programming and tactics framework where you can use F-star programs to reflect on and manipulate F-star proofs in programs. So you can write meta-programs also as F-star programs. And this is also, this kind of feature is also present in Coq, Lean, Nopal, etc. So in a way, like F-star is trying to bridge the gap that exists between these different kind of tools and aiming to provide some sort of balance between expressiveness, control, and automation so that you can write scalable proofs and programs. So in a star, as opposed to some other tools where you only validate and verify models, you actually verify the programs that you're going to run. So once you have done proofs for your programs in a star, you can now compile them to various backends and actually generate binaries and run those programs. So a star by default compiles to OCaml and F#. A subset of a star called low star that we are going to cover in this tutorial also compiles to C, and the output C code is safe, efficient, and portable. And we also have embeddings for things like assembly language this embedding is called Whale, where you do proofs for assembly programs and then compile to x86 assembly. So again, to emphasize, you actually, you verify your programs and then you compile and run them. So you actually verify the code that you're going to run. So star has been around for a few years now. We have been working on it for a few years, and there are several projects that use star for various kind of programs. HACL star is a high assurance cryptographic library, which is it's a collection of it's a comprehensive collection of cryptographic algorithms that are verified in a star and then compiled to C. And the algorithms are not just verified, but they are as performant as any other implementation out there, any other unverified implementation out there. Whale is a DSL for verified assembly programs. Evercrypt is a cryptographic provider that's built over HACL star and Whale, and it provides agility and multiplexing among different cryptographic algorithms. We also have EverParse, which is a library for automatically generating verified parsers and serializers starting from message formats. So code from all these projects or some of these projects has already found deployment in real-world software. For example, Hyper-V, which is the virtualization technology used in Microsoft Azure, is using parsers generated by EverParse. The crypto code that has been verified in a star is getting used in Firefox, in the Azure blockchain, and Linux kernel, and things like WinQuick, etc. And there are also other blockchain implementations that use a star. So a star, it's not just a research project. We have actually deployed verified code in the real world, and actually billions of users may be using it without even knowing. Okay, so with that introduction, let's get into some details. So a star, you actually write ML-like code. So if you are familiar with some functional programming language like OCaml or ML, then this syntax should be familiar. This program here is showing you a factorial function. It's a recursive function. That's the rec annotation. And the function says that if n is 0, then the factorial is 1, else it's n times factorial n minus 1. And since it's a recursive function, we can invoke the function itself in the body of the function. But although you can write this program in something like OCaml, in a star, you can do even more. You can write a specification for this function and then ask a star to verify it. So for example, here is a type that we can give to factorial. The type says that the factorial function takes an integer such that integer n is greater than or equal to 0, and it returns an integer I such that I is greater than or equal to 1. And the little logical formula in the curly braces that we are showing you here are sort of logical specifications that we want to make sure that the function satisfies. Now, once we write this spec, we can ask a star to check it. So we can invoke a star, and a star is going to come back and say that, yes, it worked, and your code indeed meets the spec that you wrote. So behind the scenes, what happens is when we ask a star to verify this function, a star is going to type check that the function body has the type you annotated and compute a verification condition that's denoted by phi here. This type checking happens in the context called gamma prelude. This gamma prelude may include things like a star standard library or any other definition that you wrote before this definition. So this includes like the context that you have currently. And then a star derives this logical formula. This logical formula is passed to Z3, and a star asks Z3, hey, is this formula valid? If Z3 says that it's valid, then the meta theory that we have done for a star guarantees that the program is safe at the type that you wrote. So we have pen and paper meta theory of a star, where we have proven that once this phi is valid, then indeed E has type T. So the type that we saw, getting more into how specifications are written, the type that you saw earlier is called a refinement type. A refinement type is basically, it consists of a base type, which is integer shown in the example here, and it refines the base type with the logical formula. So here type nat for the natural numbers is written as a refinement type over integers, and the refinement says that the value that you're ascribing this type to should be greater than or equal to 0. Now the refinements can be introduced in the type annotations, and the code remains unchanged. So you can see that this factorial, the body of the factorial function here remains unchanged, but we can give it refinement type as n:nat, and it also returns a nat. So here, this colon nat, the second colon nat is actually saying that this is the return type of the function. And what a star does is it computes logical obligations, and they are discharged by SMT automatically. So anytime a star is going to check that a value has a refinement type, it's going to check that the value satisfies the formula written in the refinement type. So the way this is going to go in this factorial example is that a star is going to say, okay, the body is if right now. So let's go to the then branch. In the then branch, we know in the context that n is 0, because that's the only case we can go to the then branch in. That's the only case in which we can go to the then branch. And under n is greater than or equal to 0, we have to prove that under n equals 0, we have to prove that 1 has type nat. And so for that, a star will try to prove that 1 is greater than or equal to 0. Z3 can discharge this kind of proof very easily. So then branch checks out. In the else branch, we have the expression n times factorial n minus 1. So there are two things to prove here. One, for the recursive call, we have to prove that n minus 1 is still a nat. And then we have to prove that the whole expression n times factorial n minus 1 is a nat. And these are the two obligations shown here. And again, Z3 can discharge them once a star provides them to Z3 in the verification condition. So refinements follow a subtyping relation. So for example, nat is a subtype of int. By subtype, it means that, so T1 is a subtype of T2 if values of type T1 can be used in a context that expects type T2. So imagine a function that expects an integer. We can always pass it a natural number, because a natural is always an integer. Whereas a context that expects a type natural number, we cannot pass an integer to it unless the integer is greater than or equal to 0. So there is a subtype relation here, and nat is a subtype of int, and this is also seamless, or it's handled by a star automatically without programmers writing any specific proof terms. So a star also has dependent functions, meaning that in the function types, the return types can mention the arguments of the function. So here is a simple increment function that says that it takes x of type integer as input, and it returns y of type integer such that y is greater than x. And note that here the type of y, which is the return type, mentions x, and such a type is called a dependent function type. And here we are using it in conjunction with refinements. So this is one type that you can give to Encode. You could even write a more precise type such that y equals x plus 1. And this is also a valid type for Encode. It's saying that the output y is exactly equal to the input plus 1. And one of the exercises is that you could try is how many other types that we can give to Encode, or can you give other types to Encode and have a star verified. We'll see this in the demo session. Okay, so as any other functional language, a star also has support for inductive types and pattern matching. So inductive types are like data types that are defined constructively. So here we are defining a type list whose elements have type A, and this type is saying that, okay, nil is a list, and then cons is a list if, and then we can build another list using cons where we can add a head to a tail. So these nil and cons are called data constructors. And this is basically defining a new type called list. We can pattern match. So given a list L, we can always pattern match and be assured that a list can either be nil or a cons. And these are the only two ways in which a list can be constructed, because that's how the type is defined. So we can write a function like map, which takes a list of A and takes a function from A to B and returns a list of B. And what it does is it pattern matches on X. So X can either be empty, in which case we just return an empty list, or if it's H colon colon T, this is called destructing the pattern. So this means this colon colon is a shorthand for cons. If it's a cons of H and T, then we apply F to H and we cons it with recursively invoking map with the tail of the list. So this is very standard in function languages. You can do this kind of stuff in STAR2. As again, this is also common in function languages or even in languages like Scala, etc. So you can write first class functions, which is anonymous, these lambdas. So you can invoke this map function now on fun x arrow x plus 2, which is an anonymous function of type int arrow int, and then apply it to list 1, 2, 3. And as you can imagine, the result of this application is going to be a list that is 43, 44, 45. So it's going to add 42 to each of the elements of the list. I think we already saw this map function was a recursive type, but just to point out, you can write this map function was a recursive function, but you can also write recursive functions over these inductive data types. So here is another type called vector. It's as opposed to list, it's also indexed by the length. So vec a n is a vector of elements of type A whose length is n. Here again, we have defined two constructors. So nil is a vector of length 0, and cons constructs a vector of length n plus 1 given a vector of length n and an element that we add to the vector. And then we can write an append function that takes two vectors, v1 and v2, whose types are vec an and vec am, and returns a vector of type vec an plus n. And the function pattern matches on v1 and appends them as you would imagine. So note that this is also here this n and m are implicit arguments. We are not showing them explicitly here, but it's a dependent function in that n and m are arguments, and the return type is using n and m. It also shows the higher order aspect of a star. So functions are just values. Functions can be input to another functions. Functions can be used as arguments. So a star is higher order that way. So the functions that we have seen so far in a star are total functions, meaning that these functions do not have side effects. They are pure mathematical functions, and they terminate on all inputs. They don't have a sophisticated precondition. They don't have sophisticated postcondition. They're just pure mathematical functions that terminate. And in a star, these functions are annotated using the annotation tote, but a arrow b is really a shorthand for a arrow tote b. So the type factorial that we wrote nat arrow nat could also be written nat arrow tote nat, and these two are equivalent. And I'm just saying, like, I'm pointing out total functions because later on we'll see that not all functions need to be total. We'll see pure functions that may have non-trivial preconditions, or we'll also see stateful functions that manipulate state. Okay, so now we can try giving another type to factorial. Let's say I wanted to give factorial a type int arrow int instead of nat arrow nat. And if we try to do that, then a star comes back with an error. And a star says, not prove that the recursive call factorial n-1 terminates. And this is indeed the case, because if we called factorial with factorial of -1, then this function is going to loop, right? Because this function is never going to come back. So it violates a total annotation because this function is not going to terminate. So int types in a star are unbounded. They are really mathematical integers. So to do to disallow this kind of program, so a star, here you see that disallows writing int arrow tote int annotation on factorial. A star uses what is called semantic termination checking. And what it means is that a star is actually going to enforce that your function must terminate on all well-typed inputs. So for that, star has a star imposes a well-founded ordering on expressions. These are the built-in ordering. So natural numbers. So basically, any types that are well-founded, that have a bottom element, they can have this ordering. So natural numbers, the bottom element is 0, so they are related by less than. Negative integers are not related because there is no bottom. You can go up to -infinity. Inductive types are related by subterm ordering. So if I know that a list is cons to 3, then I know the cons to tail, then I know that tail is less than L. So inductives are related by subterm ordering. And you can specify lex tuples such as A, B, C, where it means that so to check that a list ABC is less than A1, B1, C1, it exposes that they are less than in the lexicographic ordering. And we also have a f of x less than or equal to f built in inside a star. So using this well-founded ordering, a star builds or bakes the termination condition into the verification condition itself. And again, this gets discharged by the SMT solver. So in decreases, again, we'll see examples of this in the demo. In decreases, you can specify arbitrary expressions. Here is an example of the Ackermann function, where we are telling a star that in the recursive call, check that m and n, check that the decreases clause is m semicolon n, which means that in the recursive call, either m decreases or m remains same and n decreases. And this is a well-founded ordering, so this code verifies. Now, by default, a star takes the ordering as ordering of the non-functional argument. So we could, in this case, we could have omitted this decreases annotation, and a star will pick it up automatically the same decreases annotation. Okay, so before I go further, let me see if there are any questions. Why is rec needed for recursive functions? Can the compiler figure this out by? So this is very standard in function languages. Like even if you see OCaml, etc., there is an explicit rec annotation. I guess it guards against mistakes that you make. So you explicitly request the compiler or the type checker to make sure that your function is recursive. Can we write something like hyphen ret int or just primitive type predicate? No, so you can write arbitrary expressions in the refinements as long as they are pure. So you cannot write effectful arguments. We'll see it later in the talk, but you have to write. So you can write it as long as some other function is a pure function. I guess that's it. Okay, so moving on. So we have seen how do we refine value types. So we added refinements and we saw how a star discharges those. But we can also, a star has a notion of computation types separately, and we can refine computation types also to write specifications. So there is a distinction between values and computations in a star. Values are like total terms. Values are things that don't compute. These are just values. And computations are things that compute, may have effects and whatnot, may have preconditions and so on. So in a star, there are value types and computation types are separate. You have value types as int, list of int, all these are value types. And then you have computation types that denote expressions, which can be pure, divergent, stateful, throwing exception and whatnot. And a star has an effect system where the computation type C captures the effect of the effectful code. So there is pure code, which is not effectful. Tote is that we saw is an example of a pure code. And there can be code which is effectful, like divergence is an effect. It could read, write, state. It could throw an exception. And the star is a primitive effect system where the computation types explicitly mention what's the effect of of the term. And the effects have an ordering built in. So pure lies at the bottom, and pure code can be lifted to any other effect, but other effect cannot be part of the pure. So for example, if I write a stateful function, this stateful function can call a pure function, but a pure function cannot call a stateful function. So there is an ordering in the effect hierarchy. So dependent functions, the function types that we saw earlier, have the general form of them is x colon t arrow c. A star is called by value, so the arguments have value types. Here t is a value type, and the return type is a computation type c. And whatever the effect label of c is, this function may have that effect. And there are two forms of refinement types. One we have already seen, refinement of value types, which we saw, for example, NAT, and refined computation types, where you can write specifications along with the computation types. And we are going to see that next. So we saw this type NAT arrow tot NAT. Here we are refining the values, but we could equivalently refine the computation type. So pure is a computation type in F star. And this type equivalently could be written by adding pre and post conditions to pure. So pure takes two more arguments, a precondition, which is written using requires, and a post condition that is written using ensures. Requires is a precondition on the arguments. So here requires says that x must be greater than or equal to 0. Ensures is a predicate on the return value. So it says that if y is the return value of the function, then the function guarantees that y is greater than or equal to 0. So in a way, we moved refinements from value types to computation types and use them in the specifications. This is the most general form of computation types in a star. The pure is called here, the pure is called the effect label. Then int is the result type, and then there's a specification. And here, for example, requires and ensures are the specifications. Most of the examples that we see in this tutorial are going to be of this form: the effect label, type, and pre and post conditions. Although of late we have increased the expressiveness of a star that you can have these arbitrary indices and specifications with the computation types. But in this tutorial, we're not going to look at that. Now, tot T is just a abbreviation of pure, where it has a trivial precondition and a trivial postcondition. So tot is just an abbreviation for pure. Okay, now coming to how to structure proofs, or what are the different ways of doing proofs in a star. So there are two ways, or at least two ways: intrinsic and extrinsic proofs. The intrinsic proof is one where we encode the properties of interest in the type of the term at the definition site. So when we wrote factorial, we encoded in the type of factorial that it returns NAT, a value that is greater than or equal to 0. Now we could have added other specifications to the here, and all those styles are called intrinsic proofs, where when we write the definition, we prove properties about it at the definition site. Another way of doing it is to say that, okay, I'm going to write the definition at a very simple type, which is not going to encode, say, properties or sophisticated properties of interest. But then I'll separately prove those properties by reasoning about the definition of them separately. So as long as, this can be done only for pure functions, because pure functions can be reasoned about using their definitions. They are pure math functions, so we can reason about that. And that's called extrinsic proofs. So if I were to write extrinsic proof for factorial, I could say that, hey, factorial returns an integer, and then I could prove separately that the integer that it returns is greater than or equal to 0. That's called the extrinsic style. And so, for example, consider the append function over lists. So here's a function that appends two lists, xs and ys, and it does pattern matching on xs. If xs is empty, then return ys. Otherwise, destruct xs and append the tail with ys, and then add the head to that return list. Now, if I'm interested in proving, so for example, one property that I may be interested in proving here is that the length of the returned list here is equal to the sum of lengths of xs and ys. And if I wanted to prove that, now I can prove that separately as a function called append length. This function is a pure function. It returns unit, which means that, so unit is a type that has only one inhabitant, the unit value. So this type really has no information. Its return type is just like, has no interesting payload. But in its post condition, it tells me that length of append xs ys is equal to length xs plus length ys. And the way this proof is going to work is we are going to reason about the definition of append function separately. So just to go into a bit of more detail here, the proof follows the structure of append. So we do pattern match on xs. If xs is empty, then what is our proof obligation? Well, then we need to prove that length of append empty ys is equal to length of empty plus length of ys. Now, if you, what a star plus z3 is going to do is they are going to unfold the definition of append, replacing xs with empty, match empty with empty. Okay, so we just return ys. So the left hand side here will become length of ys. The right hand side is similarly going to unfold the definition of length. Length of empty will be unfolded to 0. So the right hand side would also become length of ys. And so this case of proof checks out. We go to the other case, that is x : xs prime, where x is the head and xs prime is the tail. So similar to how you do proofs by induction, we are first going to invoke the induction hypothesis. So we call the function append length with xs prime and ys. Calling this function again gives us the post condition for the tail of the list in our context. So we now know that length append xs prime ys is length xs prime plus length of ys. And this is our original obligation. And once again, if we just unfold the definitions of length and append, then we eventually see that we are going to reach the proof. But the thing is that you don't have to do all this. So all this is written just to explain how the reasoning is happening in say a star plus C3, but all that is done automatically. So you just write this code and the proofs will happen automatically in this case. So this is an extrinsic proof of the property that length of appended lists is sum of their lengths. Now this kind of pure unit requires ensures is a very common pattern. So we have a syntactic sugar for it and it's called lemma. So instead of writing pure unit requires ensures, you could have just written lemma ensures and it desugars to pure unit requires ensures. But otherwise, yeah, it's just a shorthand. Okay, so here we'll see in the demo session that we could have proved this property intrinsically also. So here we technically did not need a separate lemma, but there are cases where actually lemmas are unavoidable, and proving the involutive property of the reverse function, that reverse applied twice to a list returns the same list, is one such proof. It's also there in the tutorial, the online tutorial, by the way, so feel free to check it out there as well. Later on, but here the proof has to do another induction and has to use this lemma rev underscore snop for the proof to go through. So in this case, yeah, we cannot do without writing a lemma. But so here we invoke the induction hypothesis and then we invoke the lemma to get additional logical context as preconditions. But there's also a facility in a star where we can add patterns to lemmas. So what this means is that when I write a lemma, I can tell Z3 that fire this lemma whenever you have a term that mentions reverse knock LH. So whenever in Z3 is, so the way Z3 is working is it has a bag of terms that it's working with, it has a goal. And if the bag of terms contain reverse knock LH, then it's going to fire this lemma and use the fact that reverse knock LH is H : reverse of L. And writing this SMT pack means that in our actual proof, we can omit the call to the lemma. And this is going to automatically fire. So the proof for rev and volutive looks a bit cleaner. But it's also has to be used with extreme care, because these SMT patterns, if not used properly, can make Z3's proof search go in the wrong directions too. We just wanted to mention it, that it's possible to do this. Okay, so now going back to what we have in the tutorial, I think with this kind of a background, we should be able to do exercises such as proving sum of n natural numbers is n times n plus 1 by 2. So this is in the GitHub repo, in the tutorials GitHub repo, this is one of the exercises where we write a recursive function sumrec, we write a total function with this formula, and then the exercise is to prove that sumrec of n is equal to sum of n. It contains an admit. So this admit is in a star is basically saying that, okay, believe me that there is a proof, but I'm not going to do this proof right now. I'll come back to it later. So this will verify for you right now, but the exercise is to remove the admit and actually do proof for this lemma. I'm just going to mention it very briefly, but we are not going to see too many examples or details of this in the tutorial. But it's also possible to do proofs by constructing explicit proof terms. So what we have seen so far is doing proofs with proof irrelevant terms, where the verification condition just goes to Z3, and that's where the proof happens. But what you could also do in a star is to construct proof terms explicitly. For example, this is showing preservation and progress for simply typed lambda calculus. And here we want to make sure, so basically simply typed lambda calculus is this calculus for computing functions. And one of the things there is that well-typed programs should not get stuck. You should always be able to make progress, or it should be or you should have reached a value. So this progress function is exactly stating that. It's saying that, okay, if I give you an expression E and a type T such that E has type T and it has a precondition that E is not a value, then return to me an expression E prime and an evidence that E steps to E prime. Now this evidence so far, what we have seen is kind of it was in the logic, right? We were giving it to Z3 and then Z3 was proving it, but we can also make these kind of evidence explicit in a star and construct terms of type step and return them from this function. So it's called verifying using using extrinsically or explicit proof terms rather than through Z3. So as I said, we are not going to look at this this kind of proof more in this tutorial, but again, the online tutorial has examples of this sort. So please feel free to take a look at that. Okay, so I am close to ending this first session. Before we go to the demo, the last thing that I want to mention here is use of interfaces. So in a star, you can write interfaces to enforce abstractions. For example, here is, so for example, I may be writing a stack library, but I want to keep the implementation of how I represent stack internal or abstract from the clients. And this has several advantages. For one, the clients will be, as long as the clients do not depend on the representation, I can change the implementation of stack library in whichever way I want, and the client code does not have to change. So it's in a way, it gives you representation independence. Secondly, it can also be used to enforce security properties. And we'll see example of this later in the talk, where if clients do not know the representation of the stack, they cannot do, so as to say, insecure things. And maybe in stack, it does not make that much sense, but we'll see later examples where this actually is very critical to enforce security. So in a star, you can write interfaces and their implementations, and interfaces hide the implementations. So here is an interface for stack. It's saying that, okay, there is a type stack that exposes these functions. It's a stack of integers. So it exposes a value empty, that's of type stack. It exposes functions like isEmpty, push, pop, top, but you don't know anything else about stack. You don't know how it's implemented concretely. So a client of this interface is going to say, okay, I'm going to open the stack. So this is by open stack, you mean that it means that the stack interface is now in your context. And you can write some function by checking is empty s, and then you can work with the interface that's exposed to you. The implementation of stack could implement stack as a list of integers, and this is actually one of the other exercises in the tutorial GitHub repo. And there it asks you to implement rest of the interface, and then we also provide a stack client, and then you have to enhance the interface so that stack client can verify as is written today. Now, as the advantage of writing interfaces is that a bad client cannot peek into the representation. So here is a bad client who took a stack but tried to compare it with empty list. Remember, the good client was using isEmpty function that was exposed by the interface, but this client is directly trying to compare it with empty list. And this code is not going to verify, because when you open stack, you only get the interface in context. You don't know about the implementation. So this is a typing error, and clients really cannot depend on the representation of stack. And that's the abstraction via interfaces feature in a star. Okay, so I'm going to drop into some demo right now. So I hope you can see my Emacs buffer. So Emacs, we have a Emacs plugin for interactively doing star proofs. The VirtualBox image that we provided to you has Emacs installed and Emacs plugin installed. So you should just be able to open any star file and the plugin should kick in automatically. So there is a file there called demo.fst. So if you go to the directory, open Emacs demo.fst, then you should get a similar interface locally. So now we can start to verify it. So every star code is structured into modules. Modules get other modules into context by opening them. And then there are vals and lets, as we have seen. So the way to start verifying it is the Emacs plugin has various shortcuts. So if you go to *lang *mode.el repo, there you can see all the shortcuts, but the ones that I'm going to use are, so you take your cursor somewhere and then you say Control-C, Control-Enter, and that's going to start * on the buffer. Now, I don't know if this is visible, but the verified buffer is shown in this light blue background. And what we can do then is to take our cursor forward, do Control-C, Control-Enter again. It's going to verify just the chunk, just the additional chunk, and we can keep going like this. To revert, we can just go back up and do some editing, and that's going to revert until that point. So now I don't have any function verified. Here I have incur function verified, but I can go back, start editing, and I don't have incur verified again. So the command is Control-C, Control-Enter. So you take your cursor anywhere and you say Control-C, Control-Enter, and that verifies that chunk. Okay, so this is the incur function that we saw at the beginning of the talk. Here is nat arrow nat type for it. As I was saying, you can give it some other type. So I can say, I think this type also we saw. So I can say y equals x plus 1 and ask star to verify it. It should. I can try to give it an incorrect type. I can say y equals x plus 2. And now star comes back saying it could not verify. It gives an error that shows up in the Emacs buffer below. And this red squiggly tries to help you with the error location where the verification failed. So here the verification failed because y is not equal to x plus 2. We can make it back to x plus 1. We can write other types. For example, I can write x greater than 1 implies y greater than 2. And this will work out. Now, as to what we had a question earlier, suppose I write let x, I can write another add function equals x plus 1. And I can say y equals add of x. And this will verify. So I can write, as long as things are total, I can write them in the specs. So you can try writing other specs and play around that if those specs are correct as you expect. Okay, so this is the factorial function that we wrote. This verifies, but if I try to change the annotations from nat to int, then this thing gives an error. So if I remove this expect failure, if I comment it out, so this is a comment syntax, then I get the error squiggly telling me that n-1 and the error saying could not prove the termination of this recursive call. And this expect failure is an attribute, and it's star also has an attribute mechanism. So this is the syntax for attributes. And here it's saying that, okay, now a star, this definition is expected to fail. So if it fails, go ahead. So now if we verify it with the attribute, then a star allows you to go ahead. So now we can carry on. This function expectedly fails. So we also use the length function. So this is like pattern matching on the list to compute length of the list. So note that it's a recursive function, but a star automatically figures out the decreases order. So it's tail is always less than L. So a star says, okay, tail decreases. So that is fine. So we also proved a property of append. Length of appended lists is sum of their lengths extrinsically, but here is the proof that does it intrinsically. Okay, so it takes two lists L1 and L2. It returns a list M, and we added a refinement here saying length of M double equals length L1 plus length L2. And this proof goes as you would expect, and this proof also verifies. So this is an intrinsic proof of the same property. Now, you may be wondering, when do you use intrinsic proofs versus when do you use extrinsic proofs? I think it's a matter of style. There is no clear-cut guideline. But if there is a property that is simple, and anytime you use the function f, you are going to make use of that property, then better prove the property able to you when you use function f. Whereas if it's a complex property and you're not using it as often, then you should use it, you prove it extrinsically and call that extrinsic proof or lemma only when you need it. Otherwise, this property will be in your context lying around, like, making the proof context heavy and not being used. So that's one guideline, but it's really a matter of taste, and there is no clear-cut guideline there. Okay, so here also note that this append intrinsic is also a recursive function, and a star figured out that tail is decreasing when you call. So L1 decreases when you call it. But we could have written an explicit decreases clause, which said that, okay, L1 is the list that we expect to decrease. And this thing verifies. But even decreases clause can be arbitrary total function. So I could have said, hey, length of L1 is something that decreases. And this thing also verifies. So decreases clause can also mention arbitrary pure functions, and a star will make sure that those functions decrease when you call during the recursive calls. And if I try to say, hey, length L2, then this is going to come back and give me an error, because the length of L, because we are calling the recursive call with same L2, and its length does not decrease, it remains same. So this thing errors out. But since a star is automatically able to prove it, we omit the annotation from here. Now the Ackermann code that we saw, so the previous syntax that we were writing, this, when we have just one element in the decreases clause, then we can write using this syntax. If we have multiple elements, then we use this percentage list syntax. And here it's saying that either M decreases or M remains same and N decreases. So it's really a well-founded order on M and N combined. And this thing verifies, and if we try to, so as I mentioned in the talk, if we try to remove it, even then the code verifies, because that's the default order that a star picks, which is the lexicographic ordering of the arguments of the function. So yeah, so actually there are, so this demo is in the exercises. There is is there a way I can hide this thing? Cool. So there are stack exercises. So in the folder stack, you see stack.fsti, which is the stack interface that we saw. You see stack.fst, that is an exercise for implementing the stack interface. And there is a stack client.fst that is actually not just using the interface, but trying to prove some properties about stacks that it's manipulating. So this assert is a way of checking assertions within the program. So this assert function takes a proposition and F star will try to verify that this assert goes through. So right now, since we don't have the interface is not strong enough to prove this assertion, so this would fail. And the exercise is to make it so that this function verifies. And the kind of things that it tries to prove is that if you push 3 on empty stack, then the stack is no longer empty. And if you pop an element, then actually you pop the topmost element that you pushed, and these kind of things. So this is the other exercise. And in all the cases, like, you should just be able to launch Emacs within those directory and work with them. Okay, so that's the end of the first part, which is introduction to F star. I'll see if there are questions. Yeah, sorry, I also noticed that the bracket before SMT pad should have closed. Was just a typo. What kind of properties can't be proven in F star? So F star is it's a higher order dependent type theory. So you can actually encode properties, or you can write infrastructure that can encode properties of your interest. So it's higher order dependent type theory. It's very explicit. So even if, for example, you may not be able to prove today in using existing libraries, something like computational complexity or something, but you can always build an effect for it. You can always build program logic for it in S star and then prove those properties. So S star also allows you to build your custom program logics to be built in and used. So effect system of F star is extensible. It can be used to encode additional logic. So you could do other things as well. Do we see subgoals of a proof when doing proofs in F star? Yeah, so this is yeah, it's not that user friendly, unfortunately. Sorry about that. So if you do metaprogramming, if you're doing proofs via tactics, then you do see proof subgoals. But in these kind of SMT proofs, you don't see subgoals. So the way we do it is we try to write assertions and see what is F star able to prove and what is F star not able to prove, and then try to do it that way. Actually, another good source of information is in the GitHub repo. If you see, there's a wiki. We maintain a very comprehensive wiki, and here it's actually a good resource for these kind of things. So if you see, I think there is a sliding admit verification style, a wiki on sliding admit verification style that actually outlines the kind of things that we do when the proof is not, when the context is not, or the failing assertion is not available to us. What is zero in type? Yes, F star has a, that's exactly right. So F star has a type hierarchy like Coq. We have universe polymorphism, and so yeah, that's the type 0 universe. What sort of ID support exists? So we have Emacs plugin that most of us use, that most of the F star developers use. VS Code, we do not have a, we may have a plugin, I'm not sure. You can see F star lang if it's there or not. Somebody was working on it, but I'm not sure if we have an actual working plugin for VS Code. Yeah, unfortunately, like Emacs is the one that most of us use, so we know that it works. I have not used VS Code. I'll breeze past the Vim is better than Emacs comment there. Can F star prove properties about interaction between two processes? Excellent question. So F star so far has not had support for concurrency and distribution, but this year we have started to work on it, and we already have a paper in ICLP 2020 where we built foundations for concurrency in a star. And we are currently working on, this project is called Steel. So you may find some experimental code in ULib, experimental. There are a bunch of Steel files there. So what we have done so far is we have built a foundation for concurrent separation. So we are going to do this, we are doing this via concurrent separation logic. So we have built foundations for verifying concurrent separation logic programs. We are just working on, right now we are working on like building it so that people can, so that the proof experience is good, so that folks can use it. It's usable. There is like infrastructural support. So it's in progress right now. We are making progress on it. So it should be available soon. Okay, I think can expect failure be used to subvert other failures and continue? So actually, yeah, expect failure, it suppresses the failure, but that definition is also not available for use later on. So when I said, so if this, I hope this screen is still available. Please let me know if it's not. So this factorial int is not available to the rest of the function. So if I try to say, hey, test equals factorial int of 2, then this is going to fail and say that factorial int identifier not found. So expect failure is just like a demo or a testing thing. You can't really use it in actual developments. So how is append length related to append? So append length is a property about append. So anytime, so suppose you call append function, and at that time you need a fact that, okay, the length of the return list is equal to sum of lengths of the input list. Then you can call append length as a lemma. And now append length is going to give you that fact in your logical context, and you can use that to prove other things. So append length, think of append length as a property of append that is proven separately from the main append function, and it can be invoked either explicitly or by SMT patterns, as we saw. Okay, so I guess we have taken most of the questions. So why don't we take 5 minutes break and start in 5 minutes? So it's.
Wasim, you want to start at what? 2:05?
2:05. So it's 2:01. Right now on my laptop, we start in 2:05. So 4 minutes.
Okay.
Okay. See you in a short while. So yeah, so this session is going to be about, we are going to see how to verify low-level programs in a star. So far we have focused on like functional language stuff like pattern matching, inductives, general proof techniques, etc. In this session, we are specifically going to see how to verify C programs in a star. So. Okay, so remember that we saw this slide in the previous session where a star has differentiates between values and computations. Values are unconditionally total terms, whereas computation types mention effect label. And we saw the pure computation type, that's the computation type for pure code. There are, I very quickly mentioned divergence and stateful computations, and we are going to focus on them in this session. And just as a reminder, F-star effect system has a built-in effect hierarchy where pure computations can be used in other effects, but other effects cannot be used in pure computation. So there is a built-in effect hierarchy, and it's built in only in that, like, if you define your own effect, which you can tell a star where does it fit in the hierarchy. Okay, so the first effect that we're going to see is called the divergence effect. So far we have seen only pure code, but that terminates, but not all programs terminate, and we don't want all programs to terminate. For example, maybe I want to write a factorial function that diverges on negative values, and a star allows you to do that by providing you a effect called divergence effect. And if you annotate your factorial function with this dv effect, then int arrow int annotation is going to succeed. Recall that when we did int arrow int with tote, it failed because that did not terminate. But here we said we are telling a star that divergence is okay. So int arrow div int would succeed. And some useful code is, like, just to motivate why we need this, some useful code is really not always terminating. Case in point, like evaluator for lambda terms, we briefly mentioned STLC. In untyped lambda calculus, you can actually write lambda terms that do not terminate, and their evaluator is going to be in div effect. And there are other, like, infrastructure things, like web servers don't terminate. So divergence is a useful effect. Coming back to pure code cannot call potentially divergent code, but I think this question came up. Only pure code can appear in specifications. So if I write factorial as a div function, I can no longer use it in these specifications. So if I try to write type tau equals x colon int, and I try to write a refinement such that x equals factorial of -1, then a star will complain, saying that I expected a pure expression. You can only write pure expressions in specs, but I got an expression with an effect. So this is going to fail to type check. This sub-effecting relation, which we already talked about. So tote t is a sub-effect of div t. So any divergent computation can call non-divergent computation, but not the other way around. So you can write an expression that is Encode 2 plus factorial of -1 and give this whole thing a type dv int. So factorial is of type dv int, Inker had type tote, but a star will transparently lift it to div for you and type it as dv int. So that's the effect, that's the divergent effect. Now a star provides another effect called stack, and this is the effect that is used for low-level programming. So what is a computation in stack effect? So think of stack effect as being a model for a well-behaved subset of, have some C code. I want to verify properties about it. I want to verify functional correctness, memory safety, arithmetic overflows, these kind of things. So what you would do is you would write that C code in a star using the stack effect, and then compile it to C after proving all those properties. So stack effect is, if you're familiar with Horst-style reasoning, then it's a Horst-style effect where its signature is stack A pre-post. So again, A is the, so this is actually also the signature for pure. So A is the return type, P is the precondition, post is the post condition. But here precondition is a predicate on a data structure called mem, and post condition is a predicate on mem arrow A arrow mem. So this mem is provided in the star standard libraries. Think of it like a model for C memory. So this is encapsulating how C memory evolves. So it has a notion of stack, it has a notion of heap, and that all is encapsulated in mem. And stack computations are mem transformers. They are working on this ambient memory that is around, just like C programs. So pre is a precondition on the input memory, post is a post condition on the input memory, the return value, and the output memory. And you can use pre and post to write specifications, and then a star will check that your programs meet those specifications. So just to clarify more formally, what does stack A pre-post mean? So if an expression E has type stack A pre-post, then the guarantee is that if you run E in an initial memory S0 such that S0 satisfies pre, then either E diverges, so stack includes div. That is, stack allows divergent programs. So either E diverges or E terminates and returns a value V and the final memory S1 such that post S0 V S1 is valid. So this is how you should think of the semantics of stack A pre post type. If you start in an initial memory that satisfies pre, you either diverge or you return a value V of type A and a memory S1 such that post condition is valid. And we'll use these pre and post to specify all sorts of safety and correctness properties. Okay, so as I already said, it's partial effect, so it includes divergence. And if you were to go back in the effect hierarchy, then div A is a subtype or sub-effect of stack A. Now, in addition to stack, for low-level programming, the standard libraries in star also provide libraries for machine integers and C-like arrays. So remember that one of the comments that I made in the previous session was that int type by default is mathematical integer in star, but when you're writing programs or low-level, when you're writing system programs or low-level code, you're actually manipulating, most of the time you're manipulating machine integers with specific bit widths. So star has low-level libraries for those. So star provides machine integer libraries for different bit widths. The precondition of the library API enforces that it's safe to use and call these functions. So the pre and post, so the preconditions are going to enforce that there are no over or underflows. And that's why, and since once you call this function, it will be a proof obligation on you to prove that it's safe to do this operation. And the post condition of the API established functional correctness. So all these machine integer types provide a coercion called V that gives you a natural number or a mathematical natural number view of the machine integer. And you can use this V coercion to write specifications. So for example, take this add function that's part of the uint32 library. It's written as, it's implemented like this. So it takes two uint32s A and B. It returns another uint32. Its precondition says that if you view this A and B as natural numbers, then their sum, which is a natural number, and since it's a mathematical natural number, it has arbitrary, it can go arbitrarily high. It should be greater than or equal to 0, and it should be less than or equal to 2 power 32 minus 1. So in a way, you are proving that your code does not have overflow and your code does not have underflow either. And the post condition says that V of C is equal to V of A plus V of B, which is the functional correctness spec, saying that the natural number view of the returned value is equal to the sum of the natural number views of the inputs. So that's the functional correctness spec, and safety is in the preconditions. Similarly, in div, if we are trying to divide A by B, then the precondition enforces that B is not 0, and post condition again provides functional correctness in terms of natural numbers. So these libraries are in a star for low-level programming. Finally, there is a library for model of C arrays. So by the way, when I say model, I mean all these things are just implemented, are implemented in a star. So there's no assumption or axioms here. We have implemented all this in a star and made it available as libraries for client programs to use. So this buffer library is a model of C arrays. It models a well-behaved fragment of C array semantics. The type is buffer of A, where A is the element type. There's an abbreviation L buffer that is a buffer of length len, and it's defined as just this refinement. Buffers are like C arrays, but in the logic you can view them as functional sequences. So sequence is this is a pure functional data structure in a star that gives you indexed access, and this as seq is giving you a view of buffer B in memory M as a sequence. So you can use this sequence view of the buffers to write your functionals or functional correctness or other specifications, and we'll see examples of this. The library defines, so these are the basic types. Libraries defines APIs to read and write the arrays. And these APIs have enough preconditions that enforce safety checks so that when they are translated to C, then your C code is safe and free of any low-level errors. And in the post conditions, it specifies correctness specs that you can use to prove your own specifications. So for example, here is the type for read. It takes a buffer B and an integer and a uint32i. It enforces in the precondition that buffer B should be live in the memory M. So M here is the input memory when you're calling read. So B should be live, that is, it should be allocated. And the index that you're giving should be less than length of B. So in a way, we are enforcing both temporal and spatial memory safety, that there are no, that B is actually allocated and you're not accessing B out of bounds. The post condition here is saying that the returned value X is equal to the ith value in the sequence representation of B in memory M0. Okay, so we are writing functional correctness specifications on this buffer viewed as a sequence in the memory M0. And this is the functional correctness spec, and you can use this spec later on to prove some property of interest that you may have. Okay, so this is actually an interesting type. This is a valid type. This is safe because its precondition is strong enough, but turns out that its post condition is not strong enough. It's actually quite weak. And the reason is that it's not saying what's the relation between M0 and M1. Just given this function, M1 can be any arbitrary memory. So we don't know what all this function did to M0 to give us M1. We don't know anything about M1 in the post condition. As a result, what's going to happen is if I have a client function, say client, that has a buffer B, and it does read of B and in X, it can no longer prove that B at index 0 is still 0. So suppose we knew that sequence.index of as seek M0 at index 0 was 0. We can no longer prove it because the read function did not tell us what is M1. M1 could be any arbitrary memory. The read function could have written all the buffer indices. It could have zeroed them out. It could have written 1. We just don't know. So this is very imprecise. And we need to enrich our post conditions so that we can do these kind of proofs and we can reason about more precisely about what happened to M1. So for that, the buffer library provides what is called the Modifies Theory. And using this theory, you can precisely track what got changed. So in the read, for example, we actually don't need Modifies Theory because read does not change the memory. So note, we can just enrich the post condition to say M0 is same as M1. So read is just pure read-only operation. But if I wrote an update operation, the update API, that enforces spatial and memory safety as before. It gives you a functional correctness spec, but it also tells you that modifies 1, B, M0, M1. And what this means is that we are actually telling that between M0 and M1, we did not touch anything but B. So this is precisely saying what got modified between M0 and M1. So usually when we are writing stateful this code in this stack effect, the post conditions, we try to be more precise about what got modified so that the clients have an easier time proving stuff. Okay, so is this modifies enough? Let's see. So suppose I have a client who had two buffers, B0 and B1. And initially we knew that this should be B1, that B1, actually let's just call this B1 and B2. Sorry, there's a typo here. So initially, suppose we knew that B2 at index 0 is 0. Then we update B1 at index 0. Now we want to prove that B2 still at index 0 is 0. And turns out that this proof is not going to go through as is. Because the reason is that we have to tell a star that B1 and B2 do not alias. And this is common, like when you are manipulating pointers at C, often you have anti-aliasing invariants and anti-aliasing properties in mind. And a star is kind of forcing you to make them explicit. So if you wanted to prove that after updating B1, B2 did not change, you have to tell a star in the precondition that B1 and B2 are disjoint. And once you add it in the precondition, then you can prove that B2 did not change, because a star will know that B1 and B2 are disjoint. You call update on B1. The post condition is going to tell you that update only modified B1. So we know that B2 in the output memory is same as B1 in the input, same as B2 in the input memory. So now this proof will go through. So usually modifies and disjoint kind of are the two main invariants that have to be carried along in this stack effect. So if you are working with multiple buffers, then it becomes important to be explicit about which of these buffers are disjoint and which all buffers are modified by a function, so that you can reason precisely about their contents. Okay, so all this, the stack effect, the machine integer libraries, the buffer library, all this together is what we call as low star, which is you can think of it as a shallow embedding for C programs in a star. And if you write first order code in low star using these libraries, then we have a compiler called Kremlin that will extract this code to C. Now, in this extraction, the proofs and specifications will be erased. So there's no runtime cost for these proofs and specifications. So since proofs and specifications are erased, they can also be arbitrary higher order star programs. Like only the computation code has to be first order. Otherwise, you can be arbitrary higher order in the proofs and specifications. So proofs and specs are erased, and library types and APIs are mapped to corresponding C constructs. Like U32 becomes UM32_T, buffer.read becomes like just indexing an array, update becomes an assignment. And since we have done all the proofs in a star, now we know that these operations are safe in the target C programs. The C code that we emit is portable, efficient, and readable. So efficient, I mean that no runtime checks. So since we did all the proofs statically, the code is, our compiler does not introduce any additional runtime checks. And we have a meta theory that guarantees that the C code is safe and satisfies the post conditions that are proven in low star. So we have an ICFP paper on this where we introduced low star and did and the verification methodology, and there we proved the theorem that that the output C code is safe. So it's listed on starlang.org, so you should feel free to check it out. Okay, so so that's pretty much what I wanted to cover. Before wrapping up, I also want to cover constant time integers. So so this is also like a prelude to what Marina is going to talk about next. So we are going to look at how to implement crypto algorithms using in low star, and Marina will tell you about more about that. But in crypto algorithms, we are typically dealing with secret keys, secret data, and so on. And if we are not careful about operating with them, then we can leak secrets via side channels. For example, if your code does branching on the secrets and the two branches are asymmetric, one finishes very quickly, the other takes a long time, then an attacker who's observing how much time it takes for your code to run, they can infer what the secret value was on which you branched. So when you write this kind of code, you have to be very careful about operating on secrets. So similarly, if you use secret data as array indices, then attacker who's able to observe the memory access patterns may figure out something about secrets. So in low star, we have a way to fix this. We have a way to get around this and make sure that our code is side channel resistance. And it goes back to abstraction that I talked about in the last session. So the key idea is that export secret integer types as an abstract type. So we have a library that implements secret integer, but the library only exports an interface, and the representation of secret integer is not known to the clients. So what this means is that the clients can no longer use secret integers as, let's say, booleans, or they cannot use comparisons because this type is just abstract to them. They don't know what the actual representation is, so they can't manipulate it arbitrarily. The library provides constant time operations for equality checking comparisons. These libraries are in a way written by written by like experts in this, like Marina and others, who have written these libraries with carefully so to make sure that these operations are indeed constant time. And since the type is abstract, the type safety ensures that clients, as I said, cannot branch, etc. And this methodology is also part of our ICFP 17 paper that I mentioned before. We have proved a theorem that once you program in this fashion, then your code is indeed free of certain kind of side channels until C code. So our guarantees are up to until C code, and after that, either you use a compiler like ComSert-CD, which gives you constant time compilation to assembly, or you use some static analysis, or like it's beyond that, it's on C compiler to preserve this property. And all HACL algorithms, like all the crypto algorithms implemented in HACL are using these constant time integers. So they are all side channel resistant. So dropping onto some code again, if you see in the tutorial GitHub repo, there is a directory called low star, and that directory is set up so that it contains appropriate make files, etc., to generate C code and compile it. So if you just type make in that directory, so if you just type make in the directory, then that should compile everything and generate C code and try to compile the C code and generate a library. So there is a file called Verycryptflowstar Basic, which is basically like an introduction file where you can play around with different things. So here is a test function that does not have a precondition, but it has a post condition that says it did not modify anything. So it starts with push frame. So push frame, I'm not shown in the slides, but think of it as a low star construct to tell the compiler that this function will run in its own stack frame. So then this function allocates a stack array B of length 2, where both the indices are initialized to 0. Then it reads index at index 0, then it tries to assert that we read a 0 value, then it tries to update, then it tries to read again, assert again, and so it's kind of like a toy example that you could play with, and you can verify this code, and it will, as before, Control-C, Control-Enter. I was trying to look at this menu, but it doesn't seem like there's a menu option to verify. So now a star is launched, it's verifying all the libraries, and now it verifies this test1 function. So the next function is, it does not take this much time. I think since screen sharing, etc., takes a long time. The next function is interesting. It's trying to determine whether two input buffers, B1 and B2, are equal. So what the precondition says is that, okay, both the buffers should be live. This is basically temporal memory safety. We are using L buffer here, so we know that the buffers have length len. And then in the post condition, it says that we did not change the memory. And if we return true, then the contents of B1 and B2 in H1, which is the output memory, are same. And note that since we already said H0 equals H1, it doesn't matter if we use H1 here or H0 here. Now, we could write a implementation for this function that's recursive. So you could imagine doing like, okay, I'm going to compare the 0th index. If that's equal, then I'm going to recurse, else I'm going to just return false. But what I've written here is the implementation that I've written here is using a loop combinator. So we also have, in our library, we have loop combinators for various kinds of loop, like for, while, for interruptible and whatnot. And these loops are special in the sense that they are recognized by the compiler. So if you write your code using for, then this will be extracted to C for. If you write your code using while combinator, it will be extracted to C while. And the combinators expect like invariants and a thunk, and yeah, you can look at this and get more familiar with it. But The EQ buffer here is using an interruptible for, where the for loop is going over all the indices and comparing each index. If at any point x1 is not equal to x2, then we interrupt and return. Otherwise, we just keep going. And if you see the extracted code for this, which you should be able to build by just doing make in the directory. So here is the extracted C file on the right hand side of my buffer. So if you see the test1 function, so here's a test1 function in a star, here's a test1 function in C. Note that all the specifications went away, so we don't have stack, requires, ensures, everything went away. The function allocates a stack array and then assigns it, and that's it. Right? All these asserts, etc., just evaporated. We don't have them. And this EQ buffer that we wrote, there this for combinator that we used from one of the libraries compiled to for loop in C. And here again, all the specifications and proofs and assertions went away, and we are just left with plain old C code, which is proven to be safe, and no null pointer exceptions, no, I don't know, dangling pointers, no use after free, no arithmetic overflows. So it's safe and efficient C code. Okay, so that's what I had in mind for this session. Maybe we can look at if there are questions that need to be taken up. How do we encode symmetric properties like Dijkstra's algorithm returns shortest path in a graph? Right. So to do this, one thing you could do is, okay, you define a graph data structure, then you define shortest path as a spec. Like, what is the spec of the shortest path? And this specification may not be an algorithm; it's just a logical way of saying what a shortest path is. Then you implement Dijkstra's algorithm and you try to prove that the path that the algorithm returned satisfies the spec. So you first write a spec of what the shortest path is, you write the algorithm, and then you prove your algorithm meets the spec. Yeah, I think as Karthik said, it may not be easy, but that's the general recipe. I assume the notion of memory considered in stack effect is a model of sequential consistent memory that is stack built in, or you roll on own effect or for a weaker memory model. So we are not talking about concurrency here. First of all, it's all in the context of single threaded code. So we are not dealing with concurrency in the stack effect. Stack is built in, but you could also roll in your own memory model. So as I said, a star is extensible that way. So you can write your own memory model. You can define your own state effect that manipulates this. And in fact, we have examples of this at scale where we defined our own memory model, our own effect. So you can do that. Stack is not built in. I mean, it's built in the sense that it's provided as part of the standard library, and our compiler, Lowstar to C compiler identifies it specifically. So it's built in that way, but it's implemented. It's built in, it's in the standard library, but it's implemented and realized. So you can see the implementation of it. Rate shouldn't also ensure that M0 equals M1. Yeah, I think we covered it. Thanks. The key idea. How do you ensure that your hardware is constant time? Yeah, so that's outside the scope, I think. Here we are only ensuring that the code that we are writing is constant time by ensuring that you cannot branch on the secrets and you cannot use them in comparisons. Right, so that's a good point. The example of buffer equality that I showed is not constant time. And because this was using public integers, it's not using secret integers. If you look in, so there is also a checkout of HACL star and a star in your VirtualBox image. So if you go to the HACL star repo lib.buffer.fsti, here there is a function called buff eq mask, which is doing equality of buffers of constant integers. And if you see how it's implemented, that implementation is not using comparisons. It's just doing bit masking and at the end creating a mask which is either 0 or 1 depending on whether the buffers are equal or not. So the implementation that I showed is not constant time. So the real advantage is we are not just proving memory safety. We are also proving, you can also prove functional correctness. So for example, if I copy a buffer B1 to B2, which is actually one of the exercises in the repo, then you can actually prove that not only your code is memory safe, you do not access B1 and B2 out of bounds, but also the contents of B2 at the end are same as the contents of B1. And you can prove that your code did not modify B1. So you can prove more interesting functional properties that you cannot do in Rust. So it's since we are working in a logical setting, we can write these properties, functional correctness, you can prove security properties, and you can prove much more than you can do in Rust. Okay, I think that pretty much covers it. Constant time equality for arbitrary types or for just primitive types? So our library only handles primitive types right now. But if you see buffer equality that is written, I think that's also written in a way that it's constant time. But I think the idea is that these constant time libraries are written by experts who know what they're doing. And as a client, you should just use them rather than define your own. Okay, I think I'll stop there this session. Marina, when do you want to start? Up to you.
So as expected, in 10 minutes, we will have break now.
Okay. Yeah. So we'll start at 2:50 India time in 10 minutes from now.
Okay, yeah, in 10 minutes.
Okay. Thanks, everyone.
Thank you.
Thanks for joining and asking interesting questions.
Yeah. Hi, everyone. Thanks, Asim, for the introduction to F-star and Low-star. And now we are going to talk about HACL-star. I'm hoping that you're still following the talk. As a reminder, there is a Zulip chat where you can ask a question about this project, so please do it. I'm Marina, a PhD student at the Prosecco team at INRI Paris, working on the HACL-star project, which is a growing library of verified crypto algorithms, such as Chachapoli, SHA-2, HMAC, HKDF, Virtu519, and hopefully coming soon, generic BigNum library. This project is developed as a collaboration between the Prosecco team, Microsoft Research, and Carnegie Mellon University. The code in HACL-star is implemented and verified in F-star and compiled to C via the Kremlin backend For the code, we prove memory safety and functional correctness against a mathematical specification which also written in star. And we provide secret independence. Our toolchain produces a readable portable C code, which performs comparable to handwritten C code libraries. So the goal of today's talk is to show how to build a formally verified code. So when you start writing your crypto code, you first go to some crypto standards like RFC or NIST, from which you will extract a pseudocode. Sometimes you need to make an effort even at this step. Finally, you're trying to implement it in some programming languages like C, where you will end up adding more details like memory allocation, implementation of finite field arithmetic, where you can so easily get wrong. Also, you will add some optimization like vectorization, some fancy big number algorithms, and so on. After all, you will get the code in a few hundred lines, and you might think whether is your code correct with respect to specification or not, and we call it functional correctness. Whether your code is memory safe, and is it resistant to the timing attacks? So we want to have all those guarantees for our code. For this, you might want to use the HACL, which has the following programming and verification workflow, where you start as expected from defining your formal specification written in pure star. Then you will need to write a stateful code in a low star, which is a subset of low star, where you independently can prove properties about memory safety and such resistance. So you can go this path of our verification workflow, and then of course you can prove functional correctness that your code meets formal spec. Once you verify, you can compile it to C with crown in the end, but even at this step you can fail since some of the construction might not be supported by Kremlin. But at the end, you will get verified C implementation. So as you might see, all this requires a lot of manual effort, and we are trying to identify patterns that allows us build libraries and share some code and verification efforts, so that from one implementation you can get implementation for different platforms, like for vectorization, and also for we can share implementation for different algorithms like Black2B and Black2S. Let us take a deep look at how to actually write a formally verified implementation of crypto algorithms in star. And it seems that Poly 5 is a good candidate for our example, since it contains field operation, where we need to discuss how to represent large integers. Also, it contains polynomial evaluation, where we need to prove that some invariant holds for the loop. And in the end, we will do a quick tour at how it looks like in a star. And at the end, if you want to try it out, you will get an exercise. As you probably notice, there's materials that chicken in the repository, so you can already open them and follow the talk. So Poly 5 is a one-time Mac function that takes a 32-byte key and a message of unbounded length and produces a 16-byte tag. How to compute this tag? You will need to split a key into 158 integers R and S, where R should be clumped. Then you need to split an input message into 16 bytes block encoded to the field element. And then you will need to evaluate a polynomial over the final field, where the modulus is known. It's P is equal to the power 130 minus 5. from where you can see the name of this algorithm. And in practice, the Horn's method is applied, so you can easily simplify this expression, and you will get the same result as the formula presented at this line. And finally, you will compute model addition of Ackermann and S. At this talk, we will mostly focus on polynomial evaluation. For this one, we need to have some encoding functions. So first, if you take a look at the polynomial evaluation, you can see that we need to define finite field with addition and multiplication. As we already know the prime, we just say that is this big number, then we define what is FLM in our setting is. It's the natural numbers that bounded by this prime. We will introduce natural element 0 and 1 for addition and multiplication. Since we need some conversion function that allows us to convert bytes from our element representation and vice versa, and we call them encode block and encode last, since the last block could be partial. The next step is polynomial evaluation, where we define a loop combinator that we call repeat blocks that splits the input message into blocks, and for each block it calls polyupdate one function. It just applies addition and multiplication operation that we define at the previous slide. And for the final block, it calls polyupdate last function. So we can take a look at a star specification, and for simplicity, we ignore the last block, which is partial. So on the right side, you can see the high-level specification of poly. The first part is is the definition of finite field, and then we will define a polynomial evaluation. So it's quite the specification is quite short. It's 47 lines of the code, and it uses our HACL library. So you will need to take a look at looping types, loop sequence, and loop byte sequence, and we will see more usage of this in the next examples. So are we ready for the Volstar implementation? Not yet, since we are dealing with 130-bit integers. Since prime is 2 to the power 130 minus 5, it means that we need at least 132-bit to store. And how we are going to represent these integers? We all know that any number can be represented in some base R. Since it might have a few representations for the same number, but in different base, we need to have the evaluation function that converts us from this representation to the natural number. And the classical examples are binary, octal numeral system, and for unsigned machine integers, it could be unit 62, unit 64, and so on. And in the above example, we have a restriction that I at should be bounded between 0 and R. That gives us a unique representation, but we can lax this condition, and in this case, it will allow us postpone carry propagation. But it also means that we can have a different representation for the same element, even in this base. So we need to define what does it mean to be an element in a reduced form. So just I at should be in this range from 0 to R. So let's stick with radix 2 in the power 26 representation for the field element. The evaluation function will look like this sum. And then let's take a look how binomial operation look like in our new representation. So for binomial addition, we just need to expand the definition of A and B of our two elements from finite field. And we need to rearrange this formula so that we will get the coefficients that stands before r in the power I. And we'll get, as expected, thanks to the properties of natural numbers, I at plus B at. And for multiplication by scalar, it's also so easy when we need to multiply our FLM with BI. And we will get for Ri the coefficients II multiplied by BI. Multiplication by scalar and then binomial addition, you also get this simple formula. For binomial multiplication, yeah, it's requires a bit more experiment, but we all know this formula for these coefficients. But we still need to remember that we work on the finite field, so it means that we need to do at some point a model reduction. And since we know this prime in advance, we can do some optimization, like for r in the power 5 mod p, we know that it's equal to 5. So it means that when we multiply our element by r and then perform model reduction, we will get kind of a shift and we need to multiply. So from I4 goes to the end and multiply by 5. So our model binomial multiplication will look like this. We don't need to store it's with 10 elements, for example. It's enough to have 5 elements, since we cancel out our R and R2 powers. So far, so good. Yeah, we define our operation on natural numbers, but in the real world, our coefficients should be stored in machine words. So it means that our coefficients are bounded with the size of machine word, and we need to make sure that all our computation won't overflow. It means that for these coefficients, it should be enough place to store them. So we will have such restriction on them that we could easily get. And for binomial multiplication, we don't really want to compute it. Since we can ask SR to help us to infer these coefficients. And how does machine integers look like in HACL? You can take a look at lib.intypes.fsti file, where we give a definition of secret and public machine integers. It means that for secret machine integers, it just has an abstract type and we don't know the implementation, so we can have access to these numbers. But for the public integers, we use star integers, and we say that it's just some models from lib library. And then we define all our operations like addition, modulo addition, multiplication, shift right, and so on. Generically, that depends on T and L, which is in type and secrecy level. So how are we going to represent our elements in F star? As we already decided to stick with radix to install 26 representation, we can use tuples. It will be a tuple of 5 elements where we decided to use UN64, but we could also use UN32 because it's enough for our setting. But when we do multiplication, we will need to use byte multiplication. It means that when we multiply UN32 by UN32, we will need to have UN64. And when we multiply UN64 by UN64, we will need to UN128. So. But to simplify this example, we will take UN64 like for FLM and for FLM byte element. And we define our evaluation function like this in star, where power 26, power 52, and so on is just some constant in star that is equal to the representation. Since we need to track how many bits we use in our extra space, it means that if you use 26 bit for our representation, it 6 bit left for unit 32, and we will get 64 as a factor of these equations. And each element should be bounded by some numbers. Just in the end, that we could infer some boundaries for multiplication and make sure that we won't overflow at each step. So how binomial addition will look like? We say that we will use the bank operator of addition. It means that we need to prove that our addition won't overflow. So the result is in this range in unit 64. And we have the following boundaries. For example, for F it's 2, 2, 2, 2, and for G it's 1, 1, 1. I will explain from where we'll get these numbers. It's just addition and multiplication should be part of polynomial evaluation, and we could easily say that we encode this message from bytes to F element with factors 1, 1, 1, and then we perform addition that will give us we perform addition with accumulator that has invariant through 2, 2, and 2. And if you will add these numbers, you will also need to add these cofactors that you will get 3, 3, 3. And this line says that functional correctness is the following of this function. And star actually is able to prove it itself, but it needs some help. One will need to call lemmas saying that you can put modulo p for this argument f and g. Other than that, it could easily prove as not in terms of estimate, not in terms of eval. And you don't need actually compute modulo reduction immediately for addition. So you can perform first addition and then multiplication. And then you will need to do some clear carry step. And for multiplication, as we already decided not to infer generic boundaries, we say that we know these inputs for F, R, and R5. R5 is just a precomputed value for vector R. Since we multiply by this element and we can efficiently precompute this value. And the result of multiplication is FLM byte fits since we multiply unit 32 by unit 32 and we'll get unit 64. And if you know these boundaries for each function like multiplication and multiplication then addition, we can infer the boundaries for the result. You will get this one. And you will also need to prove functional correctness that in this case requires a lot of math reasoning. And starting. So you can take a look at Lowstar implementation. It's in example poly directory. You can see the following files like spec.poly, HACL spec.poly with lemmas. As you already see how level specification is spec.poly, we can define how it looks like in low-level specification, which is also pure star. So you can extract it to see, but since we are using this as tuples and Ackermann has nice mechanisms that eliminate these tuples, it will produce an efficient code. All this you already seen at slides. You can have a look, and then there is a style which you can use to prove something like. Here we pass and saying that R has following restriction that FLM fits should fit this form, and you can use band operator, and a star will able to prove that the result also will fit 555. So you can check it. And for the following function as addition and multiplication, we don't put this restriction since it's a bit complex to prove, but you could do it. And we also have clear carry steps that give us from FLM bytes FLM. So you have a file called HACL.spec polylemmas, where you prove functional correctness of these functions that we defined before. And we also enter this fits boundaries for our elements. Yeah. So this is quite easy. You just call some lemmas from a star. And for example, if for addition you can change boundaries and it will complain that it doesn't know something. For example, if we object like this, it goes through. And if you change here to 3, it will say that it couldn't prove something. Yeah, assertion fact. So you could just say that someone. So you can see that we all proving with natural numbers, and then sometimes we need to say that we are good to unfold it. Yeah, you can take a bit look. And then finally, we have imp poly.field. Since we define everything using tuples, we can just call them, and Kremlin will unfold. And the final part is imp.poly. Oh, it's open on the left side, sorry. Where you can step-by-step prove that encode block is the same as defined in the specification. So from 16-byte block, we'll need to get our element from finite field that has the following postcondition. And we say that our buffer is F and B alive, they're disjoint, and we prove that we modify only F, and we have the following functional correctness. Then we need to provide the implementation of poly 1305 update 1 function. It means that we will just call encode block. Then we define addition and multiplication function in HACL imp poly.field file that has this condition in terms of our f-add and f-mal functions. And at the end, you will need to prove polynomial evaluation function, the main one that contains repeat I loop. So it means that you will need to have the following precondition that for our accumulator, it satisfies this predicate, which just says that it's F1 fits ARC 2, 2, and 2, but we could just get more restricted condition on it, on this one that will allow us to do more optimization, but it doesn't matter right now. We need to prove that this function returns us the same result as the function defined on the right side, poly 1305 update multi. And how we are doing so, we have the correspondence between our libraries that we are using in our pure vault. I will show the summary of this, like lib types, lib row types, lib sequence, lib byte sequence. And for this one, we have the correspondence. So lib types we could use in both vaults. For lib sequence, we have lib byte buffer. And for lib byte sequence, we have lib byte buffer implementation in Lowstar. So all this operation has already proven functional correctness, memory safety, and so on. And we can use for lib loop combinators repeat I, lib.loop for function. Since we're dealing with a bit complex invariant, we need to say that we need to provide this invariant. And we also say that our invariant keeps proving at each iteration that it's equal to repeat I. And in the end, when I is equal to NB, we will prove that this first condition of this function fact. And as an exercise, you can take a look at Gemini and write a verified implementation. We are already checking some helpers to successfully complete this work. You can take a look at spec and HACL implementation that contains some holes, and you need to provide an implementation, improve functional correctness, memory safety. And you need to take a look at the following files, since this cryptographic algorithms look similar to CHT20 or SHA-3. It's cross-platform permutation. You can get some inspiration from these files. I can show you. It's in Gimli. You have spec Gimli. Yeah, where we define, you can first go to this link and you will see the description. They provide C reference from where we extract this compact star specification. And it uses two loops like repeat I with 4 and repeat I 24. Other than that, it's quite easy to prove. And exercise is here. So you will need to provide implementation for these functions, for swap, for column round, Gimli round, and the final function. And it contains a hint, but please feel free to ask these questions at the Zulip chat. And finally, you can use makefile, just run make, or make Gimli test, and it will generate this directory with, for example, lib Verycrypt.a library. You can see the C code for poly. So we can just eliminate all these tuples and readable C code. Update multi, yeah, this function. Here we will see your Gimli implementation. So if you have any questions, we're still available for all of them at our HACL and STAR chats. So thank you. That's it from my side.
All right. I guess that was a pretty deep dive into how you can use STAR to do real crypto. How how to implement crypto and how to verify it. So you can see a lot of this code on the repo and continue to ask questions on Zulip. We'd be happy to, you could even point at a particular line in some example and say, why is it like this? And we can try to give you some explanations. There is one nice exercise, at least for you to do with Gimli, and you can try other things as well. And if you have any other more general questions on how F-star works or how the compilation to C works and so on, of course, again, just put the questions on the F-star channel on Zulip, and there will be people responding to you pretty quickly.
So I just wanted to, even in the exercise directory in Lowstar, there is a verycrypt.lowstar.fst that contains some small Lowstar exercises. It requires you to write a function. So the other one, Marina, the verycrypt.lowstar.fst, but contains exercises like writing a copy function, finding minimum in an array, and prove them to be functionally correct. So please try them and ask questions if you get stuck.
All right, so I think that brings us to the end of the F-star session, unless there were, I don't think there are too many pending questions on. So there was a question about whether HACL star is a separate tool, and it was answered there, but let me just say this aloud again. HACL star is a library which is built in F-star. So it uses the F-star tool that Asim showed you earlier and Marina has been using. It's in fact written in a subset of F-star called Lowstar, which compiles to C, like Asim explained. And so it's a, you can think of it as a case study, a large case study done in F-star. So for people who are looking to write new implementations of some lightweight crypto, post-quantum crypto, or some other crypto primitive, and you want to have a verified C implementation coming out of it, F-star and HACL star shows you how to do this. So there's a whole bunch of primitives already there in HACL star, but you might have something new to write, and you could follow the patterns in the HACL star repository and the kinds of examples that Marina has been showing you to build your own. And you know, if you have any questions, you can ask us and we can help you build your own implementations. As you can see from Marina's talk, it's not trivial. It takes some time. You have to set things up properly, but there are lots of sample code that you can use to get started. So you have your exercises, you have your tools. Go ahead and if you have any questions, put them on Zulip. So let's take a break now. We'll be back in about half an hour.
35 minutes.
35 minutes exactly with the Easy Crypt session. And let's virtually thank Asim and Marina for their efforts in explaining everything about F-star and HACL star to us. It's usually takes a couple of days to fully explain these tools, so compressing it in 2.5 hours is always a major challenge. But I'm hoping that you guys got enough out of this. Well, thanks for everything and see you in 34 minutes now.